22.54. Okay, question 22.54 just asks us to propose a synthesis, and 22.54a looks like this. 22.54a, we want to take benzene and we want to convert it to this amide. So we want to convert it to this amide where we have a carbon here and we have an acyl group on here. Well, the first thing that I notice is that if we have an acyl group, we're going to put that on there by acylation. And since we have two groups on the nitrogen, we're going to have to use reductive amination to make one of them because we don't have any other way to make a secondary amine. So let's do our first retrosynthesis step like this. We're going to have our aromatic ring, nitrogen here, and we're going to have our methyl group. And then we can just treat that with acetyl chloride. Now, the methyl group, we could install that, via reductive amination. So we'll put here reductive amination. If we had the primary amine, right? If we had this, in order to install a methyl group, we would use formaldehyde, catalytic amount of acid, and sodium cyanoborohydride. So now the question becomes, well, how do I go from here to here? And I can think of a couple of ways to do that. Maybe the most obvious to some people is that, what if you had the nitrile? If you had benzonitrile, then you could just reduce that with lithium aluminum hydride and you're done. So I would say that would be a good way to do it. Another way would be if you had benzyl bromide. So if you had benzyl bromide, you could treat it with you could do the sodium azide, make an azide. You could reduce that with lithium aluminum hydride. So either way would work. Why don't we try, instead of doing the nitrile, why don't we try using the azide chemistry? Because we've already done a bunch of Sandmeyer chemistry. So let's try going through benzyl bromide. Let's do that first. We're going to use this as our intermediate. Well, how do we get to benzyl bromide? The first thing that we're going to need to do is put a methyl group on our aromatic ring so that we'll have toluene. So we need methyl chloride and aluminum chloride, Friedel-Crafts alkylation, and that will make toluene. And we know that we can do a benzylic bromination using NBS. So if we take this and we treat it with N-bromosuccinimide, we can make benzyl bromide. So benzyl bromide, like that. Now we can treat it with sodium azide. So NaN3, and that gives us the azide. So we have this carbon, then we have N3 over here, like that. So now that we have the azide, all we have to do is to reduce that. There's a number of ways you could do it. I'm going to choose hydrogenation, so hydrogen and platinum, and that's going to give us the compound or the primary amine that we wanted. And now we can do our reductive amination. So we're going to need formaldehyde, since we only need one carbon, a catalytic amount of acid, and sodium cyanoborohydride. And that's going to give us this compound. So that's going to give us this. And then the last thing we need to do is the acylation. So install the acyl group. And for that, we just need acetyl chloride. So let's scribble that down here. Acetyl chloride, like that. And that will give us the final product. There's quite a few steps in this one. There's a lot to consider along the way. But that gives us the final product. Again, if you couldn't come up with all of this, okay, if this, or even all the way up to where? All the way up to here, really, there is an alternative method, right? If you wanted to proceed through the nitrile, what you would do in this case is step one, you treat benzene with nitric acid and sulfuric acid. That would install the nitro. Then you would reduce the nitro. Or sorry, you do the dihesitization. So you treat it with sodium nitrite and HCl. So then you have the diazoniamide. Then you treat it with copper 1 cyanide to make benzonitrile. And then you would just treat this with lithium aluminum hydride followed by water. And that would give you, then you'd end up with the amine. Okay, nothing more than that. So you take benzene, you do all this, then you end up with the amine, and the rest is going to be the same no matter what, this step and this step. Any questions about that one? Does that seem reasonable?
Could you
Yeah.
Could you have used the carboxylic acid to get to NH2?
To get to the NH2. Yeah, you could do that too. Yeah.
Okay.
Absolutely. Yeah. So you could take the benzene, right, and you could brominate it using bromine and iron 3 bromide, and that's going to give you bromobenzene. And then you would treat that with magnesium, followed by carbon dioxide, followed by acid, and that's going to give you benzoic acid. Then you would treat that with thionyl chloride, followed by NH3, ammonia. That's going to give you the primary amide, so benzamide. Then you can reduce that with lithium aluminum hydride, so LaH, followed by H2O. And that will give you the amine as well. Yep, that would work. Is that what you did, Lindsay?
Yeah, it was just like when I first looked at the problem, that was the first thing that popped in.
Yeah. Yeah, that works too. I would totally buy that. Nothing wrong with that at all. All right. Anyhow, okay, let's try the next one. So, as you can see, we're getting close to the end of the heavy synthetic part of the class. You know, there's so many different ways that we learn to make things. Let's try, and this is another one. I actually kind of scribbled down 2 ideas for this one. This is 22.54b. Same kind of thing. We want to have an aromatic ring. We're starting with benzene, and then we're installing, a cyclohexyl group. Sorry, that's not the neatest cyclohexyl group. And then we want to have a carboxyl group over here, right, Lindsay? So you could use, you could totally use green yarn to install this on here, right? Well, why don't we try that? I mean, but you could also use a nitrile and do Sandmeyer chemistry. That works too. I can think of a few ways to do this, but the bottom line is you've got to put the cyclohexyl group in first because that's an ortho para director, and you're ending up with a meta director. So no matter what, I would always start by treating this with cyclohexyl chloride and aluminum chloride, and that's going to give you cyclohexyl benzene. So this compound, and then you've really got a bunch of different options. You could do a bromination. So bromine and iron 3 bromide, like this, and that's going to give you, I don't have a lot of room there. Anyhow, then to get to here, you would use, first step would be magnesium, second step would be CO2, and third step would be H2O, or sorry, H3O plus. That's one way of doing it. You could also take this compound and you could do a nitration. So you could treat that with nitric acid and sulfuric acid. And then we'll reduce that right away to the amine. Let's choose iron and HCl. We'll just heat that up. So you would end up with this compound where you have the nitro group, para to the cyclohexyl, like that. And then you would, I did the both steps there. So we have the amine. So then you're going to diacetize. So using sodium nitrite and HCl. 1 followed by treatment with copper 1 cyanide. So that would give you this compound where you have cyanide installed, or the nitrile, I should say. And then you're just going to hydrolyze that. So just H3O plus and heat. That would totally work. So yeah, I'd say either one of those is perfectly reasonable. There's nothing wrong with either of them. Both are too legit. Let's try a couple more. I want to try question 22.57, which says predict the major product. So they just give us some conditions and a starting material, and we're asked to predict what the final product would be. So this is 22.57, predict the major product, like that. So 22.57A. Oops. So we're starting it with this compound. This is called piperidine. It's nothing that you need to really know, but in the first step, we're treating it with excess methyl iodide, and then we're treating it with aqueous silver oxide, and we're heating that up. So this is going to be a Hoffman reaction. Now remember, in the first step, right, in this step here, when you treat it with excess methyl iodide, where's my pen here? There we go. When you treat that with excess iodomethane, what you end up with is alkylating that nitrogen exhaustively. So you end up with this, right? So you have this. This is an alpha carbon attached to the nitrogen. This is a beta carbon. And when you do the elimination, you're going to be pulling off a beta carbon. So after you treat it with aqueous silver oxide, you end up exchanging the iodide for a hydroxide, and that is the base that's going to rip off this proton, form a double bond, and then you're going to break this bond to put a pair of electrons on the nitrogen. Now let's draw what we end up with very carefully. So I'm kind of running out of space here, but look, you end up with two methyl groups on your nitrogen. Okay, it's also got a lone pair. Now look, count with me very carefully. If we go with the nitrogen as being 1, we have 1, 2, 3, 4, 5, and 6. And between 5 and 6, there's going to be a double bond. So we have 1 is the nitrogen, 1, 2, 3, 4, 5, 6. And we're going to have a double bond. So that would be the product. Now, it's written in kind of a strange way, but the product would be this one, 2, 3. This is the final product. So this is a way to open up that ring via a Hoffman elimination. And you end up opening a ring at the same time. So pretty cool reaction. Next one involves the Gabriel synthesis. So this is B. We're starting out with phthalimide. So this compound here, phthalimide, which looks like this. In the first step, we're treating it with potassium hydroxide. Second step, we're treating it with ethyl bromide. And in the third step, we're treating it with hydrazine. Did anybody try this one? Could anybody name the product that's formed? It has a name, but there's a couple of names you could give it, either a systematic name or a common name. Okay, well, let's kind of go through it. In the first step, we're going to end up with potassium phthalimide, right? We just deprotonate the phthalimide to make our nucleophile. So now we have potassium phthalimide in the first step. In the second step, when we treat it with ethyl bromide, we're just going to, oops, I didn't mean to do that. We're just going to do an SN2 reaction. So we have our ethyl bromide like this. We have our nucleophilic attack, loss of leaving group, and that's going to give us the ethyl group on the nitrogen, like that. Go. And in the last step, we're going to treat it with hydrazine. So then we treat it with hydrazine, H2, H2, and that's just going to blow the whole ring apart, and we end up with this compound, which is ethylamine, or you can call it ethanamine. Either one is perfectly reasonable. And then you also end up with the byproduct, which you don't really need to worry about, but I think I had it in the slides the other day, so it looks like this. This is what you get as a byproduct of the reaction as well. There you go. So a little bit of Gabriel synthesis, a way to make a primary amine. Let's see. Next one is just some kind of old chemistry, or a little bit of practice in some old chemistry. So we start with a secondary alkyl halide, so cyclohexylbromide. First step, we're going to treat that. Why don't I just do it step by step? First step, we're going to treat it with sodium cyanide in DMSO. Well, that's definitely SN2 conditions. This is a polar A product solvent. We're going to end up with this, where we have the nitrile here. The next step, we're going to treat that with H3O plus and heat it up. That's going to hydrolyze the nitrile to a carboxylic acid. In the next step, we're treating it with thionyl chloride, SOCl2. I'm sure that's a reaction that nobody can forget. Looked at this one a lot in the acids, carboxylic acids chapter. And then lastly, we're going to treat it with excess ammonia, and that will give us our primary amide. Oops. There we go, a primary amide. And the last one deals with Sandmeyer chemistry again. So let's do Sandmeyer chemistry one more time. 22.57D. So we're starting it with benzene. And we're treating with nitric acid and sulfuric acid. And we're going to install the nitro first. So that's just a nitration reaction, like that. The next reaction is a reduction. We're taking it and treating it with iron and H3O plus, and that gives us aniline. So we have aniline like this. And I forgot to put the neutralization step in here. There we go. Next is dihesitization. So that's sodium nitrite, HCl. That makes the diazonium ion. So let's write out the Lewis structure of our diazonium ion like this. And the last part is to treat it with copper 1 cyanide. That is going to give us benzonitrile. Oops. There we go. So we end up with this compound, which is called benzonitrile. We covered nitrile nomenclature in the carboxylic acids chapter.